for your content that you provide. And today in particular, and the last 150 times in addition. Chris raised his hand.
Brad bringing up my presentations on Slides Google is a miracle. I am astounded. I'm going to have to research how in the world he did it. I mean, thank you, Brad. It's amazing. The fortunate thing was I put them on last night for portability. So here is an extension to the Windows 32 Fourth. As an introduction on it, let's see. I don't do questions, Christian, so you have to drop your questions away. There we go. Very good. So the why on this little project. I use statistical software packages, commercial, and most of them only use floating point in numerical matrices. The most they will do is let you do some decimal point formatting, but it's a XY grid of floating point, and that's all you get. Occasionally, some of them will gotta find the little down arrow. There we go. Occasionally, some of them will allow you to put an alphanumeric or alpha in a column. So some of them will only let you do one letter. Some will let you do a fixed 5-letter header, a 5-letter abbreviation. Very limited. But on the other hand, spreadsheets will accept any format in any cell. This is the total far out from that. So if you notice, this example here has names, it has dates, it has numbers, it has text mixed in, has a phone number in the bottom right. So that's your typical spreadsheet representation. Well, that's more than I need. So what I want is that I want to put any specific format on a per column basis. So everything in a column has identical format, but I want character, byte, words, cells, floats, strings, any representation in by column. And then I also want off to the side a default printing format for quick reports. So I really want to do a lot of interactive, enter some data, do a quick report on it before I, as a front end, before I do any processing. So that quick report formatting is quite important. So this takes me back to that old proverb we've heard before, when you have a hammer, everything looks like a nail. Well, I've implemented and presented before on this little matrix package that I use. That's the numeric only style. So to solve my problem, I'll create a matrix to specify the format of a matrix. And I'm borrowing the schema concept from database. So the schema is a super matrix above the matrix that we are using. From that, we can specify the column content, as you see the classic list there. We can specify the column width in bytes, the column offset, and then the column default printing format. So within the schema are numeric codes, as we well would imagine. And under size, the code, of course, for byte or character would be 1 at size. The 16-bit word is 2, 32-bit word is 4, floats are 8, and then strings are arbitrary length. Fixed format length, though, fixed length strings. Variable length strings is phase 2. Under type, they're just a numerical list of the different byte types. And then under format, some typicals might be 1 is pure integer, 2 has decimal, 3 is right justified, 4 is left justified, dollars, and then with commas at offsetting thousands. And this would be extensible, so you should be able to very easily add new formats. So here is an outline of it. On the upper right, we see the schema itself. And it has 3 columns. There's actually the 4th column, which is the formatting one, but for simplicity, I've eliminated that. So the first column gives us the byte offset. So where does each column begin? And each row in the schema corresponds to 1 column in the matrix. So Remember that whenever we talk about a row in a schema, each entries then are specifying what a column will do. So that first row in the schema says the offset begins at, of course, the 0 byte of the 0 cell. It's a string which has a fixed length of 24 bytes, and type 6 says it's a string. The second column is specified by the second row in the schema. And of course, since the size is 24 bytes of the previous column, this one starts at offset 24. It has a size 8 bytes wide, because it is a floating point, and 5 says floating. And then finally, at the offset of 32, we begin a column that's 4 bytes wide, and it is integers. So under the hood, a matrix is shown at the bottom right, which has strings, floating point, and fixed point. And leading into, and also at the top then it says matrix A and a number. Every matrix is identified by the 0 byte address of its allocation in memory. So the 0 byte of the 0 row of the 0 column is its locator. And every time a matrix is referenced, it's from that number. So at the top is matrix A, which is actually a value. Executing matrix A gives you the address of the matrix. Leading into that are some fixed offset parameters. Reading from the bottom to the top, which goes from right to left, we get a parameter that gives us the number of rows in this matrix. It gives us a parameter that shows the number of bytes per row. It is possible to redefine matrices, and the redefinitions are linked together, so there's a pointer to any redefinition. There's a numeric security check, so every time we access a matrix, we check the security check to make sure it really is a matrix. To be able to list matrices on an index basis, there's a link to the matrices. They're linked together. There's a pointer back to the schema, up to the schema, which we'll explore in a moment. And then there is a pointer to the matrix identifier. So with that, we're able to navigate to and from the matrix and identify all the parameters that make it function. So the schema is one level above. And it, again, has a value locator. So executing the up arrow matrix A gives us the address of the schema. And as we see before, it has those values in it. Now, in the schemas, all values are 32-bit integers. They're all 4 byte, 32-bit integers. So there is no need to do access, or parameter analysis on those. And it has the same definitions: rows, bytes, pointers, pointers, pointers. So it is defined just as a matrix would be. And if you can list a matrix, you can use the same list word to list a schema. Now, for that reason, the schema needs a schema, because when you list from the schema, you need to know its format. And guess what? There is a proto-schema. That is one level above. Now, the proto-schema, though, is somewhat different. It has abbreviated format. Notice there's a bunch of empty pointers, because we got to stop somewhere, and there's no proto-schema. So the proto-schema does need a special program to list it, and or operator to list it and handle it, because it's quick format. And it turns out it's always this way. Every proto-schema has exactly this arrangement, because the schemas all have the same fixed format arrangement. I hope that's clear. So here's how it works. The double right brace accesses the cell of a matrix. Its input parameters is the physical address, the byte address of that matrix, and the row and column you're interested in. You execute the double right brace, and you will get the address, the memory address of that cell, and then the code number, which is the cell type. And that is done by the words of a C offset and row offset and some math around that extracts both the cell address and the cell type. how this is used then is, this is our fetch sign, but with the tilde fetch, what it's saying is it's the type matching fetch. So now what comes into this is what was generated just a moment ago. We have an address and a type. So the case structure then pulls out and figures, is it a cell, a float, a byte, a character, or a word? And in that case, it takes the right fetch. So we have fetch, F fetch, C fetch, C fetch, W fetch. And then the string fetch does nothing because the string gets the physical address. So that's the magic of typed access. This is typed formatting. So in this case, we come out with the value from the previous value and the word type. And now we pick out, is it a cell, float, byte, character, or a word? And now we're picking out either dot, f dot, dot, emit, dot, and for the string, it is count type. So in those simple 3 little levels of extract the word, extract the value, get its type, pass it properly to these display routines, and you can now fetch, store, display, and so on, typed. And now Julian, Julian's last name, the guy that did the scientific fourth? Noble, Julian Noble. He had a method of doing this within scientific fourth, but is significantly more obtuse than this. It's dense. And here is a report writer. Again, it's a right brace list, give it an address, and it goes through here by dimension, by row, by column, and it uses the operators we just saw of the double right brace fetch, the tilde A and the tilde dot, and it extracts the values and prints out the report. So in 3 levels, we've accessed the cells, we found their type, we've gotten the values, and we've passed it to a report writer. And here's an example. So in this case, I programmed that little example we saw here where we had a name, we have a floating point, and we have an integer, and the fourth is happy. So the design is stable. It's early. I'm still adding and moving things around a little bit. The thing I haven't gotten to is I want to be able to catalog all the schemas and the matrices so you know what's live. So I need to be able to list not the contents, but an index or a listing of all of my resources. And I haven't done that much in report formatting. That's open-ended because, you know, we'll keep having more variation of how to report. Another one would be to have variable length strings, but that's for the work I'm doing, that isn't necessary. I'm not doing word processing. I'm doing statistical data processing, and so fixed length strings are fine. For my older matrix system, I can read CSV files, and for this newer system, I got to work out how to get CSV files in and link them up to the matrices. So that is my presentation, and I'll turn it back to our fearless leader. Thank you.
I believe the next speaker is.
Yes, exactly. Sorry, I goofed up. This is Kevin, and hopefully Peter is available.